Let's begin. Hello, and welcome to the last unit of Foundations or Principles of Engineering Analysis. It is gonna get hard, okay? The math is gonna get um, more annoying and complicated. Um, and I don't want to haze you with math. So the approach I'm trying to get to tries to balance step by step how to understand the mathematics. There will be a lot of vector calculus, and we're going to venture into tensor calculus. Now, do I need tensors to teach fluid mechanics? No, I can get away without dealing with tensors at all, and even without vectors. And in fact, once we start solving these equations, you will be dealing with the expanded forms of these equations. But there are two reasons we want to teach you the tensors is that, again, as a chemical engineer, coming out as a grad chemical engineer student, you are assumed to know some things. You come out from our program as a chemical engineer. You're supposed to know basics of fluid mechanics and mass transfer. You're supposed to know what tensors mean, what they are. Um, Even if you are not using them all the time, you're supposed to know what they are. Otherwise, it's not a chemical engineering PhD, right? So if I were giving you a degree in some other discipline, right, then yeah, I don't have to teach you tensors. But if the burden is on me to make sure that you understand, you know what these, at least you're exposed to the terminology and what they mean. And in a way, it's like just the same way that like it's not acceptable as an adult, like for example, not to know how to cook an egg, right, or like manage your money or drive, along those lines. It's not okay to be a graduate student in engineering and not know what tensors are. So it's one of the rituals of going to grad school. Now you might have seen tensors before, you might have heard of them. That's great. This will be then a second time to look at them. So I will try to keep the complexity to a minimum, but it's gonna get complex. I cannot sugarcoat it. It is what it is, and the only way to learn it is to practice it. That's it. Very simple. That's the only way to do it, is to see it over and over and over and over and over again until it becomes second nature, and then you see it next time and you're like, yeah, you know what this means, and you know how to proceed and do any calculation. The second reason is that when we switch to tensors or tensor form, there's two ways that we will present tensor forms: the dyadic form and the index form. Both of those reduce the whatever 28 terms in the equations into 5 terms. Okay, so it's also a matter of reducing complexity in the problem, and when you reduce that, you see things that cannot be seen individually in the different equations. For example, continuity, you can simplify continuity, but then you have to do it across the different directions, okay? And when we're simplifying the governing equation. So once you combine all the different directions into one equation, the only way to write them is using a tensor approach. Now this could be a dyadic approach or an index approach. You will learn those words later. But either way, you cannot avoid it. Okay, it's unavoidable, just because of the nature of fluid mechanics. Okay, so this will be hard, and you like, okay, I'm gonna tell you again. You have to keep up. You have to repeat what we've done. You have to go and put effort into every term and understand it from different perspectives. I have to spend hours when I'm designing one slide just writing out the terms and reasoning about them, like, no, this doesn't make sense. I have to rewrite it in this form and change it over and over again. So if I have to do that, you have to do that times 5, right? Because I've done that so many times and I still have to spend time to understand how I'm representing the terms. And for you, if this is the first time you see this, you need to put the effort. If you don't put the effort, you're not gonna learn it. Okay, So I have a little Godzilla here. Here be dragons. If you're into Middle Earth and fiction and stuff, so they in the old days they used to have like these maps, the Vikings or anyone from like Viking has Viking origins. Like no, okay, well, uh, I don't know, maybe other cultures as well, where there were parts of the sea that were not explored, and they would put here be dragons. It's like here be dragons, you know, and then because there's like they would die in the sea or like they would get swallowed by sperm whales and stuff, and so they would put here be dragons in uncharted territory. So with fluid mechanics, with fluid dynamics, here, there, and everywhere there be dragons. Okay, so these are the mathematical dragons we have to deal with. But this will be the last unit. Yay! The last unit of the course. Okay? So the purpose of this chapter is, if you remember in the previous unit, we looked at the balance equation and we looked at a control volume and we did a balance of what's being accumulated is equal to the net advective and diffusive fluxes coming in and leaving, plus or minus source terms, right? And that was satisfactory for something like mass, for when we or even energy, right? But when we got to momentum, something was off. I personally wasn't satisfied when I told you, oh, the diffusive flux for momentum is mu grad u. And you're like, okay, but what about Newton's second law? How does the balance equation that we derived connect to Newton's second law, which is conservation of momentum, right? And so something was off. In my opinion, it wasn't very rigorous because the balance equation comes as an afterthought after the conservation laws were developed. The balance equation is another way of looking at the conservation laws to simplify and kind of dumb down the analysis a little bit. So a more rigorous approach is to actually go after the conservation laws directly, which we've learned, and specifically Newton's second law and the first law of thermodynamics, and then develop the equations from those laws. But we have to do a few finagling and few things. I had a handyman who always tried to take shortcuts, and he would tell me, "I'm gonna finagle the wire." I was like, "What is finagle? What are you finagling?" He would like try to get the wire under the drywall so he doesn't have to cut the drywall, but he still would charge me for it. So we're gonna finagle our way to get to these equations. Well, not finagle. The balance equation was finagling. So the purpose of this chapter is to go after, to derive the fluid dynamics equations from the conservation laws directly. And what we will get is the actual general gas dynamics equations that apply to all the way from fully compressible flows to incompressible flows. Okay? So we did see the Navier-Stokes equations in the previous chapter. Those will still hold. We will rederive those, but those were just a simplification of the full equation. So it wasn't very satisfactory in that sense. We will also look at how we solve these equations for very simplified cases. So you've probably done the Poiseuille flow in your undergrad or not. This is flow in a pipe. It was originally developed to study the blood flow in veins. Poiseuille was a physician who studied blood flow in veins. He was a doctor, and so I don't know why he wanted to calculate the velocity distribution in veins, but he gave us that solution, and so we're going to derive that. We're going to derive Couette flow combinations of those, and we'll see how we can further simplify the equations. But that's going to be at the end once we're done with the governing equations. First, we will look at asking question, what is fluid mechanics? What is a fluid? What's the difference between a liquid and a gas? What is fluid mechanics? Whenever you hear mechanics, mechanics means is connected to forces, okay? When you have forces, how things respond to forces. And what is the difference between undergraduate fluids and graduate fluid mechanics? Now, a fluid, we have a sense of what a fluid is, right? We know, oh yeah, this looks like a liquid. Even when you're looking sometimes at like sand coming down from a distance, coming down in a quarry, you're like, oh, this looks like water flowing down, right? So we have a sense of what fluid behavior looks like, but there's a precise mathematical definition of what a fluid is. Specifically, a fluid is a substance that will deform continuously when acted upon by a force, specifically a shear force. So a solid doesn't deform continuously. It will deform. So when you take a piece of plastic, let's say, or a piece of metal, like an iron bar, you're like strong enough, you start bending it, it starts deforming, but then at some point, pop, it's gonna kink or break, right? Or you take a piece of chalk, it will deform very, very slightly, and then pop, it will break, right? A fluid does not break. It will continue deforming and deforming and deforming and deforming forever. Okay, and that's the distinction between a fluid and a solid. Now, what's a shear force? A shear force is not a normal force. A normal force is a force perpendicular to a surface. A shear force is a force that's not normal to it, rather tangent to it. So we can push this way, we can push that way, but it's not a normal force. Okay, so a shear force, a fluid is a substance that continuously deforms and keeps moving when subject to a shear force. The shearing stress, the word stress, is simply force per unit area. So, for example, the pressure, atmospheric pressure, Newton per square meter, is a kind of stress because it's force per unit area. It's Newton per square meter, right? So a stress is simply just a force per unit area, and a shearing stress is a force that is created whenever a tangential force acts on a surface. Like you see this hand over here, pushing, there's fluid under it, and there's a plate on top of that fluid. You put your hand on it and you slide it forward, right? And that's going to create a shearing force on the fluid, and it's going to deform the fluid. We're going to derive the solution for this case. This is called a Couette flow type problem. This is how they measure viscosity later, more on that later. Then what's the difference between liquids and solids? So every layperson understands also intuitively what between liquid and gases, not liquid and solid. So any person understands naturally, this is a gas versus this is a liquid. But there are also specific definitions. So liquids are generally composed of molecules that are more closely packed together. A solid is like they're really closely packed together. A liquid, they're loosely packed. They can still move around, not as much as a solid, but they're not packed as much as a solid, and they can move around, but they can still they can move. They don't break. They continuously deform. So the difference between a liquid and a gas is that a liquid is a type of fluid that retains its volume and will be contained by will retain its volume, but whereas a gas is doesn't retain its volume. It's just gonna occupy whatever space you give it until it is bounded by walls. Even 5 molecules of gas, they're just gonna keep spreading and floating around, whereas a liquid will retain its volume. Okay, will try to stay compact. Now obviously the boundaries are gonna set where it can go, but it will always have like a free surface. Okay, what is fluid mechanics? Then the fluid mechanics is simply the study of how fluids deform when they are subjected to forces, right? So we said that a fluid is a material that continuously deforms when subjected to a shear force. Fluid mechanics is the study how the fluid deforms, what it does, how it deforms, the rate of deformation, what it looks like when we put forces on the fluid. Forces could be normal and tangential, all sorts of forces, okay? Now, what is the difference between undergraduate and graduate fluid mechanics? So there are 2 approaches to study fluid mechanics. The macroscopic approach, that's primarily what you did in undergrad, although you might have, if you've taken fluids, initially with fluid mechanics, you did these integral balances for conservation of mass. The average of the flow coming in is the average coming out. You didn't look at the details of the velocity field. You looked at just the averages, average of energy, etc. So that is the macroscopic approach. You're looking at the entire system, not what's happening inside it. The graduate approach, on the other hand, we want to look at what's happening at every point inside the fluid system, right? So in undergraduate approach, would ask, what is my flow rate in the pipe flow? What is my pressure drop between inlet and outlet? Okay. Whereas the graduate approach would say, well, what's going on inside that pipe for the velocity as the flow is started in the pipe? What does the velocity profile looks like? And then as it moves down, how does it change? How does it develop? We can compute flow rates, but those are like secondary things, right? Because now you have details about the velocity field. And when you understand the velocity field, you can understand how mixing occurs, and you can understand how deposition occurs on the walls of the pipe, for example. One problem with pipe flow is when transporting oil and gas at very long distances. So you look at crude oil, very viscous fluids, right? There are incredible, they have a lot of impurities in them, and when transported for thousands of miles, they lose pressure, they start making depositions along the wall, right? So it starts reducing the flow, it messes up with economies, etc. So studying what's going on inside the fluid itself is very important. So that's the differential approach. And you can study fluids experimentally or numerically. We kind of touched on numerics for advection diffusion equations. Solving the fluid flow equations is much more complicated. We're not going to do it here. That's an entire CFD course, because you cannot solve them without understanding numerical methods very well. So now the question is, I'm going to go back to this balance equation where we had these three primary terms: a transient term, which accounts for how much we're accumulating of stuff in a volume. So remember, this phi was stuff per unit volume, okay? And that phi, we were accumulating it in some arbitrary small volume in space. And then we had the net diffusive and advective flux, which was given by J, which is a vector, right? Because you have advective fluxes in X, Y, and Z, and diffusive fluxes in X, Y, and Z, and then a source term. So how can we derive this? How can we tie this back to the great conservation laws? And that's the primary question. Can I tie this back to Newton's second law, to the first law of thermodynamics? Now, if you remember the great conservation laws, we had three primary laws that can be expressed in the following manner. That mass for a system, bear with me for a second here. So forget what we learned now about diffusive and advective fluxes. You're talking about, think about it in terms of physics, okay? The mass of a bunch of stars, or the mass of a bunch of particles that are moving together. The conservation of mass says that the mass is conserved, it doesn't change in time. So you can write this as total derivative dm by dt, d mass by dt, is equal to 0. Conservation of momentum, that's Newton's law. Rate of change of momentum, mass times velocity, dmu by dt, is equal to the summation of external forces. So take a car moving, accelerating, subject to drag, etc. That m times u, the mass of the car times the speed of the car. That's Newton's law. That's what's telling us that the change in momentum for that car is balanced by the external forces exerted on the car. Could be drag, friction, etc. Or the parachutist falling, right? So we know these laws, we apply them to these systems. So bear that in mind. And then finally, conservation of energy, that the rate of change in time of the total internal energy times the mass. So total internal energy times the mass, so m times E total, is balanced by the rate of heat minus the rate of work. So Q dot minus W dot, right? So that's first law of thermodynamics. How can I connect this? This has like these total derivatives, right? There's no partials, there's no gradients, there's no divergences. How the heck can we tie this back to that balance equation, or get the fluid flow equations, or all the equations we derived previously from these laws? Well, we can, but we have to define a few things first. And this is a critical thing that a lot of people do not recognize, is that the laws of physics are written for what we call a material system. What is a material system? A material system is a collection of materials that are uniquely identifiable, such as a planet, car A. You're tracking, when you apply the laws of conservation, you're applying them always to car A. Wherever car A moves, you're always tracking car A, or the blue car, or those 3 cars, or those 5 stars together, or galaxy, the Andromeda galaxy, right? You're looking at the entire galaxy. How does momentum and mass and its energy change over time? But it's still that entire galaxy. It's uniquely identifiable. You know where it is at all times. You know how it's changing at all times, right? And you're tracking that. So that's called the material system. It's uniquely identifiable. You have to bear that in mind. Now, cis in these equations, the subscript cis, refers to this material system. So when I say take Newton's law, second law, you're applying it to a material system, okay? It doesn't readily apply to a fluid, okay? Now, this approach is called the Lagrangian form of conservation laws. So all conservation laws that come from physics, they are by definition derived in a Lagrangian perspective. So the Lagrangian form or the Lagrangian perspective, you are following the material system. You're doing the conservation law on the uniquely identifiable collection of material. Okay, you can pack those material however you want. You can pick 7 cars and draw a boundary around them and say, this is my system. How does the momentum on those 7 cars change? Or when you're playing pool, right? So the billiard balls, right? So you can define that triangle as your material system. How does the momentum change in that? Then you would track all of the particles, all of the balls in that material system, but you're following those. They are uniquely identifiable, okay? Now, for a fluid system, for a fluid flow, it's a little bit more complicated. Like, what is a material system for a fluid flow? Like you take flow in a pipe or flow in a channel or a hose blowing water. You know, what is your material system? Is it all the water? Well, there's more water coming in. So for a fluid flow, a material system is a finite number of, or you need to define a finite number of fluid molecules, lump them all together, okay, and pick them and choose them and draw a boundary around them, and you would have to track them everywhere they go inside the flow. Okay, so that's the Lagrangian perspective from the fluid. So if these are fluid particles, then fluid elements, which is what we define for a fluid material system, is a collection of fluid particles. So for example, this yellow fluid element is the fluid system at time 0. I arbitrarily chose those molecules arbitrarily and said, okay, I'm going to track those molecules together. And then this is another fluid element at time t0. But then as the fluid moves and changes, I need to continue tracking the yellow fluid element as well as the orange fluid element. Now, you can imagine how hard that is because water molecules, they all look the same, right? So I would need to somehow put the trackers on each one of those water molecules, right? And be able to figure out what the yellow system is doing and then what the orange system is doing, okay? That's incredibly, incredibly complicated, okay? It's because fluids are different than solids. They continuously deform. They're composed of hundreds of billions of fluid molecules of small, most small representative piece of fluid. So to get detailed information, suppose we can do that, but to be able to apply Newton's law, conservation of mass and conservation of energy in their Lagrangian form, we would have to track a very, 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 very large number of fluid elements. So if we were to look at that smallest volume, which was 10 to the minus 9 cubic meters, we would need to track, to put that volume as our smallest fluid element. Because again, I'm trying to understand what's happening everywhere inside the fluid flow. So if I were in 1 cubic meter of air, okay, and suppose the air is spinning and mixing, I would need about 1 billion fluid elements of each of size 10 to the minus 9 cubic meters and track those as they deform, as they move in the flow. It is incredibly complex and unfeasible, even computationally, because not only you have to identify those fluid molecules and track them, you have to see how they deform, how they are deforming, because other fluid elements are bumping into them and kind of rubbing on them and pushing on them and making them spin, right? So you have to track all of that, and that is incredibly complex. Is it doable? Yeah, but nobody wants to do that. It is very, very complex, even numerically, to do that. Okay. So instead of doing that, because that's the only way we can apply these great conservation laws, the Lagrangian form. So instead of doing that, we can say, you know what? I'm not going to track all of these fluid elements. What if instead I can define a fixed region in space, okay, and let whatever fluid element go through it, but I don't care. Remember, the problem with fluid elements was figuring out how to identify your fluid elements, okay? But instead of identifying them, we can identify a fixed region in space and say, okay, instead of following all of my elements, I'm only gonna look at that fixed region in space, and whatever fluid elements go through it, I don't care. But as they go through it, those fluid elements are bringing fluid and changing speed and things and properties inside that small region of space, okay? And then instead of tracking the fluid element, I would just focus on that region of space or many regions of space and just track when the fluid elements come in, what do they bring in and what do they take out from that region in space. So now you're starting to think about advection and diffusion, okay? And specifically advection, when things come into a fixed region of space, what do they change in that region of space? Okay, and that is called the Eulerian description of fluid mechanics. In that Eulerian description, so if you were to say, to apply this, for example, to a to a pool game, or cars driving on a freeway, instead of following the cars, what you would do, you would stand and put a speed tracker and watch as the cars come by. You measure the speed at that point, okay? And then say when cars go through here, they're gonna have that kind of speed over time, regardless of what cars come in. So you are no longer tracking the fluid elements. Instead, what you're saying, when fluid elements come through that region in space, they are going to have that speed and that density and that mass and that momentum and that temperature, etc. Okay? So it's like you're inverting, you're doing a frame of reference change. You're no longer following the elements. You are fixed now in space, and you're saying all the fluid that comes through this region of space is going to inherit the properties of that region. So we can call this a control volume. It's very small, okay? You can make it as small or as big as you like, and you put as many of those as you like inside your fluid system. We're gonna put the smallest one, which is 10 to the minus 9 cubic meter. We're gonna put as many of those so we have a continuum, okay? And the surface of that control volume is called control surface. So from now on, CV stands for control volume and CS stands for control surface. So when we do our integrals for the control volume, it's gonna be the integral over CV, and the integral over the surface integral will be the integral over the control surface. Okay, good. So that's the paradigm shift, but we still have to figure out how can we translate the Lagrangian form to the Eulerian form. So before we do that, we will consider a general fluid flow with the following properties. It has a velocity field that we call vector U, and that has Ui plus Vj plus Wk. So those are the components of the velocity field. Later, we will also call them U1, U2, and U3 to describe x, y, and z velocities. The fluid has a density rho, viscosity mu, pressure P, temperature T, species Ci for the ice species, and tracer like ink as we're tracking through the fluid, just random tracer, we call it phi. Now, all of those quantities are fields. They change in space and in time, okay? So I'm not gonna track parentheses and put x, y, z, comma, t, or rt. You should assume that all of those quantities are function of space and time. They change in space and in time, okay? All right, so now how do we write the laws of physics in Eulerian form? Osborne-Reynolds, you've probably heard of the name Reynolds number. So Osborne Reynolds came up with, well, we give him the name, we give him credit for that, but really this is a physics principle coming from physics, to convert between Lagrangian and Eulerian. But he takes credit for that. We call this the Reynolds Transport Theorem. It allows us to convert a material system derivative, okay, to an Eulerian perspective things. We'll see what those are, okay? So we first need to make a distinction again, or remember the distinction between extensive and intensive properties. So remember, extensive properties were dependent on the size of the system. So mass, for example, depends on how big your system is, right? So the bigger your container, the more you can put fluid in it, the mass is gonna get larger. Okay, but the intensive property that corresponds to that does not depend on the size of the system. Okay, so in this context, moving forward, an intensive property is property per unit mass. Okay, previously when we did the balance equation, it was per unit volume, right? Right now it's going to be per unit mass, and this is actually the definition that is more rigorous, is that the intensive property is property per unit mass. So mass, the extensive property, is m. The intensive property corresponding to mass is mass per unit mass, and that is essentially 1. Okay. For momentum, the extensive property is mass times velocity. The intensive version of that is momentum per unit mass, so that will be the velocity u. So u is momentum per unit mass. Okay? Energy is mass times total energy, and then mass times total energy per unit mass is simply this specific total internal energy. Okay, total internal energy per unit mass. Now, the formal definition for intensive versus extensive property is that the intensive property is the derivative of the extensive property with respect to mass, d capital phi by dm, okay? And this is how you can see these derivations come in. If capital phi is m, dm by dm is 1. If capital phi is mass times u, then d mass times u by dm is equal to 1. So, m, I put it in lowercase here, but that's the same thing as mass, okay? That's the same thing as mass. All right. So, one more thing before we get to the Reynolds Transport Theorem. Now, I'm going to rewrite this and say d capital phi, a small change in the extensive property, is equal the intensive property times a small change in mass. So, d capital phi is small phi times dm. This is just mass. So all I did was say phi times dm, did the product of this fraction. So d phi is phi dm. Now dm is an infinitesimal mass on an infinitesimal volume. Okay, on a very small volume, dm is simply rho times dv. It's very important. It all goes back to the density. Okay, so on a very, very small volume, the density is constant. Okay, it's an infinitesimal volume. So that's your representative volume element, 10 to the minus 9 cubic meters. Okay, dm, that elemental mass, is rho dv, right? Because mass is rho density times volume. dm is density times dv, because on a small volume, density is constant. Now we substitute back here. So we take this and put it back here. Then d phi of capital phi, the extensive property, a small change in the extensive property, is equal to rho times the intensive property times the small volume, okay, dv. And finally, we can now go back to say that the total phi in your volume, whatever volume, could be a system volume or a control volume, a fixed volume, doesn't matter. The total extensive property is the integral of the small change in extensive property, and that's equal, just simply substituting the math, integral over the volume of rho phi dv. So density times intensive property times and you're integrating that over the entire volume. Now remember, rho is a function of space and time. So on the small volume, it's constant, but as you take that and integrate it over a large volume, it's going to change from point to point. Okay, it's going to change from point to point. So keep that in mind. Now the Reynolds Transport Theorem, it tells us the following. For an intensive property B, now I'm switching nomenclature. I'm not going to use phi for the theorem because that's how it's presented. They choose the letter B. For an intensive property B, so that's extensive per unit mass of a system with a corresponding extensive property capital B equal m times small b, we have the following. So that's the theorem. We're going to spend a minute on this, and I'm going to need my annotator here. Okay, where is the... Okay, annotation. It says that the rate of change of the extensive property for the system, and notice there's total derivative. Why? Because this is a system derivative. There's no change in space. You are following the full property for that system. The momentum of the billiard ball, the momentum of the car. You're not looking at the change of momentum inside the car. You're just following the momentum of the full car. So there's no change in space. It's only a change in time. Okay? So that's why you see the total derivative. And those are essentially what the conservation laws are telling us. For momentum, for example, B of the system, the extensive property is mass times velocity. Okay? Now, what I'm doing next is remember that B, capital B of the system, is the integral of rho times the intensive property times dV over the system. It's still over the system. So I didn't do much here. I just moved capital B system. This is equal to the integral of rho B dV. That's what we just derived in the previous slide, okay? Over any volume, could be a system volume or a control volume, doesn't matter. But here we're doing it for a system volume, okay? I'm just, so those two things are kind of obvious. And this is now what the Reynolds theorem is telling us. Moving from system to a control volume, this is equal to the rate of change in the fixed control volume, or in the control volume, that's the region in space that we define, of rho b dv. So again, the integral of the intensive property weighted by the density over the control volume, not the system volume anymore. Now we're switching to a control volume. And those might not be equal to each other at all because the system volume is just a fluid, random fluid element, okay? The control volume is going to be like this little rectangle or cube that we have, okay? Plus an integral over the surface of the control volume, the control surface, of the flux of the intensive property. So this is where the velocity field of the flow comes in. That's why we had to define that a flow has a velocity field u. U rho b dot n ds, what is this measuring? It's measuring the advective flux of rho b through the faces of the control volume. So what this is saying, if the rate of change of the property inside the fluid element as it goes through a control volume, what it's going to do to the control volume, there's going to be a rate of change inside the control volume plus the flux of rho b through the control volume faces. And think about it, this makes sense because as fluid elements come and leave, they bring stuff and take stuff out with them. So that second integral is accounting for that, for what it's bringing in and what it's taking out. Okay? So that's the primary form of the Reynolds Transport Theorem. Now this is important because now we can see the connection between a Lagrangian form, this total derivative on the left, and the Eulerian form, these integrals and derivatives on the right hand side. Okay, and you have these integrals over control volume and control surface. Okay, so we can simplify this a little bit more. If the control volume does not deform, you can allow the control volume to deform, but in general we don't. if it's fixed, a fixed point in space, fixed region in space, then this time derivative over here, this time derivative can go inside the integral. Now, why do I have it outside the integral here? Well, think about it. If the control volume is deforming, then it's changing in time, and I need to keep track of that. But if the volume is not deforming, then it's not changing in time, so I can bring that time derivative inside the integral. And notice what happens when I bring it inside the integral. It has to become a partial derivative. Why? Because rho and b are changing inside the control volume. They are fields, right? So I cannot, it's not a total derivative of rho and b, it's a partial derivative with respect to time, okay? So now that becomes that total derivative of the volume integral becomes a volume integral of the partial derivative, okay? Okay, so one more step. Okay, now we have on the right hand side, we have two integrals. One is a volume integral and one is a surface integral. Now remember what we did when we derived the balance equation. We convert everything to volume integrals, right? Because then we can just put them under one integral and make a statement about that. Now remember the divergence theorem. This u rho b dot n ds, that's the flux of rho b, advective flux of rho b being advected by the velocity field into the volume. I can use the divergence theorem to convert this into a volume integral. And now I have div u rho b dv, and I have only volume integrals relating the Lagrangian form on the left. Okay, so these are the Lagrangian form, and this is the Eulerian form. And this works like, it's mind-blowing that this works magically. You don't have to even specify what the control volume is. All you have to say is that to go from a Lagrangian form, I just apply this theorem and I write everything in an Eulerian form. Go from the Lagrangian form of the conservation law. All I have to do to convert that derivative on the left-hand side of the conservation law into these integrals. And now I can work in an Eulerian form. So from now on, we will be looking at points in space and how things are changing at those points in space. Okay, that is the biggest step to go from these Lagrangian conservation laws, material systems, to Eulerian form, to their Eulerian counterparts. Okay. Who has seen this before? Who has heard of this Lagrangian Eulerian form? Fiona, Ariana, you've seen this in fluids, right? Who else? Thomas? Okay. Guys, turn on your cameras if you can, please. Okay. So the others, you haven't seen this at all. Have you taken fluids? But you haven't seen this. Okay. So good. Review this. It's, in the end, it's a math conversion and integral. Okay. It's a Leibniz formula. That's what's called. But in fluids, we call it the Reynolds Transport Theorem because it's focused on having a fluid flow, a velocity field. The simplest way to think about it is say, this is just a formula to go from the conservation law of a material system, Newton's law, the first law of thermodynamics, to a form that doesn't follow a material, that just points in space. I'm just looking at how things change at fixed points in space. Okay, they change in time and they change from point to point, but you're not tracking any fluid particles, any fluid elements. Okay. All right. That's the first jump we have to make. Okay. So now remember we have these conservation laws. D mass of the system by dt is 0. D momentum of the system by dt is sum of external forces. And this energy equation, total energy equal Q dot minus W dot. Okay, and now we're going to go one by one, and we're going to start untangling the left-hand side. Okay, easiest is going to be mass conservation. The energy equation, we're going to do some of it. The rest is going to be done in mass transfer. But we're going to spend a considerable time untangling the momentum equations. Okay. So let's start with conservation of mass. It's just simply now plug and play. Conservation of mass, it says mass of a fluid element is constant. So if I take a collection of fluid particles and track them, their mass is going to be constant. Okay, that's what the conservation is saying. Okay, d mass of the system by dt is equal to 0. All right. Now in this case, B in the Reynolds Transport Theorem, right? B is equal to. So let me try something here. If I draw, so this B over here is the same as this B over here. Okay. Doesn't. Okay, I have to switch back. Lowercase b, the intensive version of mass, is simply 1. It's not rho because we're already gonna inherit a rho over here, rho b. Okay, so the intensive property version of mass is simply 1. So now I can apply this. I can say Reynolds Transport Theorem, RTT, says dm by dt is equal d by dt of the volume integral over the system, over the material system, rho dv, remember small b is equal to 1, and that's equal integral over the control volume. I'm just applying the theorem here. So I'm applying, so this one is this guy because b is equal to 1, and this one is this guy. Also lower small b is equal to 1, div u rho dv equals 0. Now, remember the argument I made when we did the balance equation. This is a volume integral equal to 0. We didn't say anything about the volume. This applies for an arbitrary volume. And I made the analogy, if I tell you integral of f of x equals 0 for any bounds, for any a to b, the only logical conclusion is that f of x is equal to 0 everywhere. So this means that the integrand itself is equal to 0, and that gives us the continuity equation. d rho by dt plus div u rho or div rho u is equal to 0. Okay, so that gives us that continuity equation. Okay, we derived this. This is consistent with what we derived before, so that's great. But that gives us the continuity equation in a more rigorous form. Okay, you're going from a material system, a collection of fluid molecules that do not change their mass. They can change volume. The material element can expand or compress, but their mass is the same, right? If it expands, the density in the material system is gonna go down. If it compresses, the density is gonna go up, but the mass will remain the same. Be careful about that. Okay? Be careful about that. The material volume, material element is changing shape. It's deforming, right? And everything is responding to that deformation, but its mass is always constant over time. It doesn't change mass. Okay? Nothing is going into it, nothing is leaving it. But the control volume is transparent. Things are coming in and things are leaving. Okay? Next, we're going to go after the energy equation because it's a little easier because I'm not going to do the right-hand side. So for the first law of thermodynamics, it says that the rate of change of the total energy in the system, okay, so you're taking just a clump of gas and just tracking their energy, is equal to the rate of heat minus rate of work done on the system, okay? And then my capital B is MET, and then my intensive property, so extensive is mass times specific internal energy, and then the intensive property is simply the specific total energy, and so that's ET, and then I simply substitute in the Reynolds Transport Theorem. So you look here, this is so this one is still in this one. Sorry, let me clean this up a little bit here. Yeah, so this is going from MET is the integral of rho ET dV, and finally this gives us this form. So this whole thing is equal to these two here. Okay, that's the Reynolds Transport Theorem. That's the RTT. Okay, and partial rho ET by partial T dV, etc., etc. Now, I'm not going to derive what's on the right-hand side because you need to have knowledge of tensors, because the stress tensor in the fluid is going to cause heating and work. The pressure is going to cause work. on the system. So without doing fluids, we can't do the energy equation before doing fluids. So we're gonna focus on understanding what fluid is doing, what the fluid mechanics are, before deriving the energy equation. But you know, Professor Sutherland and Professor Yachow will derive it in mass transfer. Okay. In many ways, the derivation of the energy equation is harder because of the terms it contains. This Q dot and W dot are very complex with fluid mechanics. All right. Now, the rest of the focus is going to be on conservation of momentum. Okay. And that's what we're going to spend the majority of these lectures. So for conservation of linear momentum, there's also angular momentum. We're not going to cover that. We're going to do linear momentum. Angular momentum just adds one more layer of complexity because you have to track angular motion. We're not going to worry about that. We dealing with linear momentum is sufficient to derive the fluid equations. Conservation law for conservation of linear momentum is Newton's second law, and says the rate of change of momentum for the system is equal to the summation of the external forces exerted on that system. Okay. Now, this is a vector equation, okay? Because U is a velocity vector field, UVW, right? And we're gonna call them X mom, Y mom, and 3 mom. So fluid flow has, fluid flow has 3 moms. A mom in the X direction, a mom in the Y direction, and a mom in the Z direction, okay? So from now on, we're gonna say X mom, that's conservation of momentum in the X momentum component. Y mom is conservation of momentum, the Y momentum component, and Z mom, the Z momentum component. And you agree that this is a vector equation here. Mu, that has 3 components. And notice here, I'm not sloppy in my nomenclature. This F bolt face is a vector because U is a vector here. If you were to put F equal a scalar here, that will be wrong. Okay, because it's not a scalar. Each component of momentum has a different force vector. Okay, if you put it as a scalar, you're saying that all of these momentum components have the same exact force, which is not true. Yeah. All right. So next, what do? How do we get the X component of momentum? You could say the X component of momentum is M times U, which is, or the Y component is M times V. Or you can dot the equation with I, J, and K. So that's the more rigorous way of doing it. So the X component of momentum is obtained by dotting the vector equation with the unit vector I, okay? And the Y, and then that gives you, when you dot it with I, the only thing that's going to be left is the U component of the velocity and the X component of the force. Okay, so F external has an X component in I direction, Y component in the J direction, and Z component in the Z direction. So when you dot it with I, you're only picking up the components in the I direction. Same thing when you dot it with J, you're picking up the component in the Y direction, and that's going to give you dmv by dt, dmv, equals summation of forces in the Y direction. And finally, in the Z direction, you dot it with K, with the Z unit vector, right? So this should be clear, right? You're taking a vector, the dot product is going to give you the component in that direction. The resultant momentum is a vector in 3 dimensions, right? To get the X component, you dot it with I. To get the Y component, you dot it with J. To get the Z component, you dot it with K. And that applies to the full equation as well. So external forces dotted with K is only going to give you the Z component of those external forces. Okay, and then that gives us dmw by dt equals summation of forces in the Z direction. We good here? So it's important you follow me at every step. If something is not clear, please just speak up. Okay, because the misunderstanding will only stack up. There's going to be a lot of symbols and a lot of subscripts, etc. So if anything is not clear, please speak up and let me know. We'll fix it right now. Okay? So this is simply taking the components of the vector equation, that dm vector u, in the 3 directions. Okay? So now I could have dealt with the vector form of the equations, but there's no, I didn't do a vector form of the Reynolds Transport Theorem. We only did a scalar form of the Reynolds Transport Theorem, right? So I can only apply right now, as far as we know, we can only apply the Reynolds Transport Theorem to scalars. So that's why I took the x component of momentum, y component, z component, because each component is a scalar, right? Rho v is, or mv is the scalar y component of momentum, okay? In and of itself, it's a scalar. So I can apply the Reynolds Transport Theorem individually to each one of those components, okay? So that's a reminder of the Reynolds Transport Theorem again here. Now notice the extensive property for x momentum is mass, I should be capital M here, sorry. Sloppy nomenclature, -1, Professor Saad, -1 on each one of those. Okay, so this should be capital M. Let me actually fix that right now. Let me fix that. And there's a reason I'm using capital M. You will see that much later. Okay. Can you see again? Yep. So the extensive property for x momentum is m times u. Okay. And the intensive property is extensive per unit mass. So that's the x component of velocity, or momentum per unit mass, which is u. The y component of momentum, the extensive property is mv. The intensive property is v. Okay, and this was the conservation equation for each component, right? And same thing for z momentum. The extensive property is mw and the intensive property is w. And now I'm ready to apply the Reynolds Transport Theorem to each component. Okay, we're going to go one component at a time. All right, we'll go one component at a time. So for this one, I simply apply the Reynolds Transport Theorem. So it's integral over the control volume of partial by partial t of rho u dv plus the integral of the control volume of div u rho u dv. Okay, now be very careful. You remember this from your homework assignment, homework 7. I told you to evaluate div rho u, div u rho u, right? This is why. It's because I'm getting you ready to be able to expand these terms. Now, most of you in that case, they expanded it and expanded all the derivatives. You should have just kept it as on the form u rho u, v rho u, and w rho u, as we will see in a minute, okay? But here I'm stressing the fact that this is a convective flux of what? This is the convective flux of the x momentum component, rho u, x momentum per unit. So this per unit volume, rho u, is x momentum per unit volume advected by the u velocity vector field. It's important to write it in this form. I know you can move the vector you could do rho u times vector u. Don't do it that way. I'm doing this on purpose because I want to distinguish what information is being advected and what is advecting that information. In this case, what is being advected is x component of momentum per unit volume, rho u, and what is advecting it is the velocity field u. Okay? Now this is equal to the summation of external forces in the x direction. Okay, so it's a scalar. It's a scalar only in the x direction. Okay. Next is the dmv by dt. Do you want to take a shot at it? By analogy to the x momentum equation. So it's integral of partial
rho v over partial t dv plus the integral of the control volume nabla dot vector u rho v dv.
Yep. Correct. Yep. So that's integral over the control volume of the rate of change of rho v over time, then that's a partial, okay, plus the net flux through the control volume, okay, div u rho v dv. Again, this is stressing the fact that you're advecting rho v. This is the y component of momentum. You're advecting rho v, nothing else, times the vector u, okay, the velocity vector u, all right? And that's equal to the summation of the external forces in the y direction, okay? And then finally, for the z component of momentum, mw, the intensive property is w, and rho w gives you momentum per unit volume. W is momentum per unit mass, rho w is momentum per unit volume, and that gives you integral of d rho w dt. And you see the symmetry here, right? And what's nice about these equations, they repeat. And if you keep things clean like this, div u rho u, div u rho w, rho v, div u rho w, and that's why it's important to not be sloppy with your nomenclature. Because if you didn't put this velocity vector as a boldface, then how do you know which is the vector and which is the scalar component, right? So you can't be sloppy with your vector notation. If you don't put a dot product over here, that's not a divergence anymore. It's something else. So you can't be sloppy. Divergence, gradient, vectors, be clear about them. It will help you more than anyone else. All right, so let's clear all drawings. This is clear now. We have three equations. One equation for each momentum component. One equation for x mom, one equation for y mom, one equation for z mom. Okay, good. Now I did this cool animation. Let's see what's gonna come next. Next, I want to talk about the advective fluxes. This quantity, u rho u, u rho v, and u rho w. And I come from a school of thought where it's very important that I write it this way. Because I know when you expand the terms, you can rearrange them. I don't rearrange them because I want to be unambiguous, unapologetically unambiguous about what is being advected and what I'm advecting. All right, so we're gonna take, so these animations took me like 3 hours just to check this out. So this comes here and then expands, right? And so what is this term? This is the advective flux of x momentum. How do I know? Because there's the velocity vector multiplying the x component of momentum per unit volume. So it's u rho u. Now you expand that, it's u rho u I plus v rho u j plus w rho u k. Simple scalar multiplying a vector. But notice I put the advecting velocity field in red, and I kept it before rho u. Some people will rearrange this and put this as rho u squared plus rho uv plus rho uw. What the heck are you advecting and what is being advected when you write it that way? You don't know. Don't do it that way. Yes, it's a simplification when you are finally trying to solve the equation. But when you are trying to understand it and reason about it, keep it in this form, because this form is clear. It's telling you what is advecting, that's in red, that's the velocity vector field, advecting the x component of momentum. Clear, simple, no additional manipulation. Okay? So you see what I'm saying? Some might come and say, and you can see it in textbooks. So for example, they write this as rho u squared, and they write this as rho uv. Why? Because rho should come before u and u should come before v alphabetically, and then this as rho uw. Well, what the heck are you advecting and what is being advected? You can't tell anymore when you do it that way. When you keep it this way, it's clear. All right? Next we come, so this is a vector, okay? Just like the advective flux we learned earlier is a vector. It's coming in. So this is interesting here because this is x component of momentum, but it's coming in from all directions. Although you're looking at the x momentum, which you think this is the x momentum, this is only in the x direction. No, x momentum is just a scalar component of the full momentum vector. And that scalar component, the x momentum component, can be advected in all directions. Just like energy can be advected in all directions. the x component of momentum, although you might be inclined to say, well, this is x momentum, there's only motion in the x direction. That's wrong. That's not true. X momentum doesn't move only in the x direction. X momentum moves in all directions. Same for y momentum. It moves in all directions. Same for the z momentum. Okay? And I'm going to trick you with this in the final exam. I'm going to construct equations that will trick you to say, no, x momentum is only going to be in the x direction. Nope, it's wrong. X momentum will move in all three directions. Y momentum will move in all three directions. And z momentum will move in all three directions. When you combine them together, all three components in all three directions, you're going to get a tensor. Okay, and that's what we're headed for. Okay, but x momentum moves in all three directions, etc. All right, next comes the advective flux of y momentum. Y momentum is rho v, y momentum per unit volume, and it's being advected by that same velocity vector field. And y momentum also moves, the y momentum advective flux, it's being brought in by the x component of velocity, y component of velocity, and z component of velocity. Next, when we draw a control volume, what is happening, you're going to see y momentum coming on x faces, y faces, and z faces, all from all directions, but it's still y momentum, okay? And finally, the advective flux of z momentum, u vector, velocity vector field, rho w, is also being advected in all three directions. Keep this form as is. Don't rearrange the terms. It will help you make sense of things. The advecting velocity comes first. The advected information comes next. So honor that. Honor that tradition, okay? And if some other professor rewrites it, tell them that they're wrong because they make it ambiguous of what is being advected and what is advecting what, okay? Now, thankfully, this is symmetric because look at this, and later we will talk about this a little bit. W rho u is symmetric with u rho w. But notice this is in the k direction and this is in the I direction. Now in the end, in the final equations, it's not gonna matter, right? But as you're building those equations, this is very important to know what you are advecting and what is advecting and what is being advected. Okay. Now comes to the divergence. Remember, we have the divergence of u rho u, divergence of u rho v, and divergence of u rho w. It's simply the divergence of a vector field. So, okay, hold on. Did I have this here? What the heck? Hold on, I'm missing a term here. Sorry. I'm supposed to make an animation here. Oh, okay, we are right here. Yeah, I didn't know why it didn't show this. One second, sorry, I had a bunch of animations. Okay. All right, so we are here. Okay, now the divergence of those components, you simply take the divergence of the vector, each vector. So u rho u was u rho u I plus v rho u j plus w rho u rho k. That's what I wanted you to simply write in your homework. If you wrote this, that was sufficient. Most of you expanded these and went to town with it. You don't have to. Just this is the form that I'm looking for. Okay? There's no simplification that you can make out of this unless you make certain other assumptions about the fluid flow. But this form, this is the cleanest and best form. This is the conservation form because it's keeps the fluxes inside the derivatives, doesn't make any assumptions about anything in the fluid flow. Okay, same thing for u rho v. So u rho v plus v rho v plus w rho v, and the divergence of that. Remember, the divergence tells us the net flux that's coming in and leaving through the surface, the net advective flux, right? And it's simply the rate of change in x, y, and z. And this itself is a scalar. Okay, so div u rho u div u rho v and div rho w is a scalar. And that makes sense, right? Because the x component of momentum is a scalar equation, the y component of momentum equation is a scalar equation, and the z momentum component equation is a scalar equation. So everything in it needs to be a scalar. And that's what the divergence does. It takes a vector and converts it into a scalar. Okay? So this is the answer here to your homework problem. All you had to do was keep it like this. Now, again, I'd like you to honor the order of the notation. Okay? You're not being any clearer by writing this as rho uw and this is rho vw and rho w squared. You're not being any clearer. In fact, you're obfuscating what this means, what the terms mean. Here it's clear. U rho w, u is advecting rho w, v is advecting rho w, and w is advecting rho w. So that must be the advective flux of the z component of momentum. All right? Now, if I take this infinitesimal control volume that I'm talking about, and I'm looking at u rho u, for example, this is I didn't define x and y and z faces. I defined it in the homework a little bit, but let me define it here. X faces are faces that are perpendicular to the x-axis. Y faces are faces that are perpendicular to the y-axis. And z faces are faces that are perpendicular to the z-axis. So when I tell you this is the flux going through an x phase, this immediately tells you this is going through the x direction. Flux going through the y faces, that's flux going in the y direction. Flux going through z faces, that's flux going through the z direction. Now, when you look at the x component of momentum advective flux, u rho u is coming through x faces, v rho u is coming through y faces, and w rho u is coming through z faces, coming and leaving, okay? So it's coming in and leaving, and those are the components. We split them up. Now what matters is the rate of change, right? Because the net flux is going to be the divergence, which is the sum of the rates of change in x, y, and z of all of those individual pieces. All right, so now we're back here, and we figured out what the left-hand side means. So now this is our left-hand side, right? So this is our left-hand side, okay? And we still have the external forces. The external forces for the x momentum, external forces of y momentum, and external forces of z momentum, right? So now on the left-hand side, we have these nice integrals. Okay, we know what this div u rho u looks like, and at least expanding it. And then we have next to figure out what the external forces are made up of. All right, so that's there's going to be some additional knowledge from experiments and observations that I have to just throw at you, but we can get through this together. I don't think I can cover much by the end of the lecture today, but we'll cover at least one external force. So external forces are things that act like from either remotely or from other fluid elements on a given fluid element, not within it. Those are things. So remember, these fluid elements are bumping into each other, they're rubbing at each other, they're compressing each other, so they exert forces on each other. Gravity, as well as the earth exists, right? It's pulling on all of those fluid elements all together. There are two types of forces, external forces, that act on fluid elements or control volumes, because it doesn't matter, because external forces are external, they're the same for fluid elements or control volumes. They look the same. There are body forces that act on the entirety of the fluid element or entirety of the control volume. Gravity, for example, is a body force. It acts on the entire body. It acts everywhere, on every molecule on your body. Okay? Surface forces, they act only on the surface of the body. So atmospheric pressure is acting on, my bald head and my shoulders and my arms, right? So it's acting on that surface and acting on my chest, everywhere, right? And it doesn't act on inside my body, it just acts on the surface. So whenever a surface is present, surface forces will start acting. Body forces, whenever a volume is present, body forces are going to act on it. Now, these apply equally. There's no Lagrangian or Eulerian form of external forces because they act the same way on a fluid element or a fixed control volume. They look the same. There's no frame of reference change, thankfully. So there's no like Reynolds Transport Theorem equivalent, okay? I will do gravity and then I'll let you go. The first external force, the simplest, we look at the gravitational force. And like I said, it's a volumetric force. And in general, a gravitation, we have to consider a general acceleration framework because your fluid could be, for example, on Earth and could be spinning in like different directions. So you might have an acceleration force, an effective acceleration in different directions. Okay, or you could be moving, in a truck and accelerating, and that's going to exert, and the fluid is going to be accelerated like a truck transporting gasoline, for example. As it accelerates and slows down, it's like there is a gravitational force pulling on the liquid, right? Kind of moves back, and then as you slow down, it's going to slosh forward, right? So there could be acceleration fields in all different directions. We'll consider generally gravity, or it could be any other acceleration field, as being three-dimensional. There's a gravitational component in X, gravitational in Y, and component in Z. Typically, we take the Z direction to be the vertical direction, and that gives you Earth's gravitational acceleration. Then the gravitational force on the fluid element or the control volume, it's V, it doesn't matter. But now, since we are in Eulerian form, we're applying this to the control volume, is the integral of rho g dv. Now, why do I need the rho? Remember, this is going to be a force, okay? So the net has to be, the result has to be a Newton, in newtons, right? It has to be in newtons. And so if you think about this, rho, kilogram, so mass per volume, and you multiply by volume, it becomes mass, times gravity, that's Newton, meter per second squared. So mass, kilogram.meter per second squared is newtons. So you get newtons. That's why you need that density here, okay? Or another way to think about it, rho g is going to be momentum equivalent to force per unit volume, okay? It's kilogram.meter per second, that's Newton, per second squared, that's Newton per cubic meter. Okay, and that is going to be rho gx dv in the I direction, I component, y component, and z component. Now, each one of those, so that's the net gravitational force. But I need each component because the x component is going to go in x mom, y component is going to go in y mom, and z component is going to go in z momentum. Okay, and those are the individual contributions for x, y, and z momentum. You can also obtain them by dotting with I, j, and k. It's going to give you the same answer. But integral of rho gx dv is going to be the x momentum contribution. Integral of rho gy dv is going to be the y. So this will be y momentum contribution, and this will be z momentum contribution. This is x mom. Okay, so x mom. This is y mom, and this is z mom. Okay? And we're done with the day. There's a lot of math coming along. My advice to you is review these. Today, I'll post the slides, excuse me, as soon as possible, and post the recording as well. But review these just at least to see what's been done. Okay? It's not going to get easier. It's going to get incredibly more complex, and the notation and tracking all of those terms is going to be harder and harder. Okay, so it's on you to catch up. I know you're in a semester crunch, end of semester, everyone is pushing all of this down on you, but I survived it and you can too. Okay, courage, all right, and courage, young Jedis, and we will get there. Okay, I'll see you on Thursday.